Assalamu alaikum. This is the continuation of our previous lecture where we are discussing various modulation scheme. So today's topic is QPSK, quadrature phase shifting. So QPSK. We have already discussed the other three topics, which is actually BPSK, binary phase shifting, ASK, amplitude shifting, and FSK. FSK, frequency shifting. So this is our fourth modulation scheme, QPSK. So the analysis will be very much similar to the previous one with a few modifications. So we will start with you see the BPSK and ASK, they are deal with a single pulse, but when discussing with FSK, we have seen that we need actually two pulse. Same thing will happen with QPSK. So we consider uh, two pulses. Okay, so consider two pulses, P1 and P2. Okay, so P1 is expressed by square root of 2 by t cos 2 pi fct 2 by t sine 2 pi fct. Of course, both are having the same condition that for 0, so this is the condition, right? So where t is the same as the previous, t is the symbol duration, and t equal to k by fc, all these things. K is the integer value, right? Now this one can be rewritten as what? You can rewrite it as a 2 by t sine 2 pi fc t plus pi by 2, right? Same thing. So we can see this is also P1. So what is the difference between the P1 and P2? So P1 and P2 both are the sine signal with pi by 2 shift. Okay, so the P1 version here, P1 is actually pi by 2 shifted version of P2. Or actually we can say in general, one pulse is actually shifted version, pi by 2 shifted version of the other one. Okay, that's why actually here our quadrature phase, because we need a phase shifting, means we had to change the phase. That's why we introduce this phase. Okay, so what should be the energy for P2? So minus pi by minus infinity P2 square t dt. So what is the energy? So 2 by t, so 0 by t sine square, sine square 2 pi fc. We're actually finding the energy of symbol P2 t dt. Okay, so of course if we solve it, we did it actually several times. So after solution we can get that this is actually, so this is actually EP, and you have the pulse EP2 for example is 1. Okay, so this is actually an unit energy. Actually this is actually our preliminary assumption that P1 and P2 are unit energy signal, energy pulse. So EP1 or EP2 both will be, so if in this is case, so EP1 it will also be 1, so that we find. So here EP2, EP2. So we know that both of the energy for the both pulse are unit, it's a unit energy pulse. Okay, so what should be their inner product, like minus infinity to plus infinity, P1t, P2t dt. Of course the inner product will also be, eventually it will be 0. Okay, so I'm not solving it. So if you solve it, then the inner product will also be 0. Find P1 and P2 of this value, this one and this one and this one, put it here in P1 and P2, find the solution. Inner product will eventually will be 0, to which will actually show that they are orthogonal. We actually have seen this phenomena to the previous case. We also call it orthonormal, because they are orthogonal and normalized to unit energy. Okay, so because it shows these are orthogonal, this QPSK, this is actually very much similar to the analog signal quadrature carrier multiplexing. Okay, that's actually an analog modulation scheme. We are not actually discussing that part here. Okay, we are more now for our case, our signal xt. Okay, so let me draw what was previously. Okay, we will draw it later. No, not now. So our signal xt is a1 p1t plus a2 p2t. Actually, in previously, this was we would be writing only one of the pulses, right? Either this one or that one. But this case for QPSK, this is a two pulse signal. Means actually the symbol contains two pulse, pulse 1 and pulse 2. That's why we are writing it. So two symbols here, two symbols A1 and A2 are modulated by P1 and P2. Okay, so symbols, two symbols, two symbols A1, A2, which is A1 and A2 modulated by P1 and P2. P1 and P2. So each of the two carries one symbol or one bit of information. Of course, A1, yeah, of course, here A1 is nothing but plus minus A. It can be either this value, also A2 is also plus minus A. We know it from the, we also know their average value A, because we actually have seen it here in our previous case EP, EP, because average bit energy, so average bit energy A is again square root of EB. So this actually we have derived it again and again and again for all the previous three cases. So energy average, this is average bit energy is square root of EB. I'm not deriving it now. This okay. Okay. So signal xt can be like this. Signal can be rewritten as this way. A1 have these possibilities and A2 also has these possibilities. So let's write like plus A P1 t plus a2 also plus a p2 t, or it can be plus a p1 t minus when p2 have like a2, and a2 also have negative value, so minus a p2 t, or it can be minus a p1 t plus a p2 t, or it can be minus a mhm, 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 p2 t. You see, because we have uh, like this combination, which will give us actually 4 set of possibilities, so we have 4 set of possibilities. You see, 4 set of like possible signal xt, possible xt. Xt can have 4 possible signals. That's why actually it is called quadrature phase shifting, QPSK, because it has 4 possibilities. Like every signal have 4 possibilities. Okay, and each symbols carries 2 bits in this case. Okay, so okay, let's see what we do in the receiver side. Okay, so this is the transmission, how signal will be transmitted. Signal in quadrature phase shifting, the signal have 4 possible combination, or these 4 can be transmitted. Okay, so we will see, we will actually took one of them. For example, this one, let's take this signal, one of the combination, and see how we can derive it. Okay, okay, so consider x, so consider the first combination, consider the first combination, which was actually a p1t plus a p2t. This was our first combination for the xt. Okay, so let me here, what is p1? P1 was 2 by t uh, cos 2 pi fct plus a p2 is actually 2 by t is sine 2 pi fct, right? So okay, let me give them individual name. Equation 1, huh? Okay, probably if this is equation 1, this is can be, this is equation 1, equation 2, or second possibilities. This is third possibilities. This is fourth possibilities. So we are dealing with the first possibilities, right? So consider possibilities 1, possibility 1. Okay, okay, now let us find. So a we need to modify this equation. Let's say this is 2 by square root of t, means one of the, so 2 is nothing but we know 2 is nothing but square root of 2 into square root of 2, right? So we write 2 here, so I have to insert or divide it by square root of t, right, to make it equal. Okay, so that square root of 2 I put it inside the bracket, and the remains cos 2 pi fct. Okay, plus for this case also 1 by square root of 2 sine twice pi fct. Right, now square root of t, this one, and this one will actually convert it to the their corresponding sine and cos term. Okay, so a, so we can write twice a by square root of t, 1 by square root of 2 square root 2, actually nothing but cos pi by 4. Okay, so cos pi t plus also 1 by square root of t is sine pi by 4. So sine cos pi t. Now this gives us actually cos a cos b plus sin a sin b, this formula, this one, cos a cos b sin a sin b. So which is actually nothing but twice a by square root of t. So we can write cos a minus b. So I'm treating this one, this a as a, so twice pi fc t minus pi by 4. Okay, so this is for what? This is for possibility 1, when this is for when xt equal to, so xt have this one, so this one, this like this one, we get a solution. So likewise, if you solve for everyone, so what we find? We find this first solution, right? Okay, so I'm not going to solve all of them, waveform 1, waveform 2, waveform 3, or possibilities 1, possibilities 2, possibilities 3. Okay, so you will do it. So we find twice a square root of t cos plus pi ct minus pi by 4. This is for first one. If you do the same solution, go on for the second possibilities, the solution will be, you will do it yourself. Okay, so twice pi fct plus pi by 4, then twice a square root of 2 cos twice pi fct plus 3 pi by 4 and twice a square root of t plus twice pi fct plus 5 pi by 4. So this is for waveform 1. Form 1. So this is waveform 2. This is waveform 3. This is for the waveform 4. Okay. Now you see this one, 2. Okay. So what is the difference between these two? Pi by minus pi by 4 to pi by 4, nothing but pi by 2. What is the difference between this and this? Nothing but pi by 2. What is the difference between this and this? Nothing but pi by 4. What is the difference between this and this? It's also pi by 2. Right? Of course, we can see it. Pi by 2 is nothing but 90 degree. That's from the name quadrature. This one quadrature, this word comes from this 90 degree, because they sorry, this word quadrature, this one comes from, because one from another differs in 90 degree. That's why the quadrature word comes. That's why it's called QPSK. Okay, we can draw this 4 combination here just to visualize it. This is one. If I draw a if I draw a circle, oh sorry, it's not a good one. Let's try again. Okay, looks like a circle, which is not actually not very good circle. Anyway, so what is the first one? First one is all amplitudes are these are all amplitude, which is actually minus pi by 4. Okay, first one is minus pi by 4 will be here. So minus pi by 4 will be, for example, here. Huh? So here, which have an amplitude twice a square root of. I made some mistake. Okay, this is twice a square root of t. So all the these are not 2. These are actually t, square root of t. So square root of square root of. So they are actually a square root of t. T. Okay. So twice a by square root of t. This is the amplitude. What is the degree? The degree is minus pi by 4. So this is actually minus pi by 4. Okay. So this is one. So the second one is this. This is pi by 4 plus pi by 4. So second one is pi by 4 with amplitude twice a by square root of t. The third one is 3 pi by 4. So 3 pi by 4 will be here, somewhere here. 3 pi by 4. Of course, the amplitude is twice a by square root of t, and the degree is, this is 3 pi by 4. The fourth one, 5 pi by 4, which will be this one, which will be here, somewhere here, like this one. Of course, twice a by square root of t, and the degree actually this one, which is actually 5 pi by 4. You see, we have actually this 4 constellation, or the waveforms of this quadrature waveform. We can actually draw this constellation nicely because we already know it. So where so the constellation, so let us draw here. Okay, the constellation diagram, the constellation means these 4 possible points. Constellation diagram. So constellation diagram will be this is plus a, this is minus a, this is plus a, this is minus a. Remember, we actually find, okay, we find this angle, like for this equation, different angles based on what? Our previous assumption, this assumption of this one, for various a values, so we can plot this. For this is actually same way, the way the degree represents here, the way the degree represents, also the same thing is the constellation. So our first constellation will be, for example, here, right? We already find the amplitude. Second constellation will be somewhere like here. Third constellation will be somewhere here. The fourth constellation will be somewhere here. This one is denoted by AA. This is actually minus a. This is actually a minus a, right? And this is minus a. That's actually our, each point we can actually can give the name, right? So this will be a p1t plus a p2t, isn't it? So this one can be given as name a minus a p1t plus a p2t. The second, this is the our first combination. This is the second combination. This is the third combination. This is the fourth combination, right? So you can write individual signal. So this will be actually our a p1t minus a p2t, and this is actually minus a p1t minus a p2t. Okay, so this is the constellation diagram. Okay, so now this is actually the signal will be transmitting, na? So what will be happen in the receiver? So receiving signal, you see the procedures are same, eh? We transmit the signal, then we look on the receive signal, then we find the optimal decision rule, then we find the beta rate. So same thing every time, we follow the same step. So receiver receiving QPSK. What's happened now for our again let us take the signal xt for the first waveform or the first possibilities. Okay, so a1 p1t plus a2 p2t, right? So what happened in the receiver? In the receiver, the signal has to go through what? HT, right? Our LTI response of the low pass filter, isn't it? So it can be either it pass through H1T, it can pass through H1T, or this signal can pass through H2T. We know H1T equal to P1 T minus tau, and H2 is P2 T minus tau, right? We discuss this like we are discussing this again and again. We also discuss this for, of course, for this one, the solution would be A1 EP. Of course, EP is 1. This is for the signal when it pass through, plus the noise will be n tilde, and for this one the solution would be A2 EP plus n2 tilde. We actually, without solving this equation, we can easily guess that this will be the output. By what? Because we know the previous solutions. Of course, we can prove it. We can prove it. Okay, let's see. Eventually, it will end up. So match filter with. So this signal xt signal will be. So xt signal matched filter filtered with respect to what? H1T, which is actually P1 T minus tau. What will happen? What will happen? A signal goes to, for example, this is xt signal. Of course, our signal always has a noise, additive white Gaussian noise, we know. I am writing this nt, this figure again and again every time. This is yt, so yt, but it goes through ht, ht in general. So this goes to ht. This is our like standard receiving signal. So what's happened when xt signal matched filter with respect to h1? I mean, we assume, okay, if the match filter is h1t, what happens? We know yt, so we can write this signal yt is nothing but xt plus n. We, where n is the additive white Gaussian noise, blah blah blah. We actually reading it several times. So what is xt? Xt is nothing but a1 p1t plus a2 p2 t plus nt. We are saying that this x signal, this signal, this yt, which is actually this one, this will be match filter with respect to h1. Okay, so okay, so if this is the case, if this is the case, then x1 signal match filter with respect to as to what will be the signal. So yt signal will be complex conjugate with the ht, right? Actually, sorry, the yt signal is passing through ht, means it's actually convoluted to the st. Okay, what will be the output? Then it is actually this part is xt, so we can write xt into ht, right? Here we are doing with respect to h1t, that's why h1t. So plus like we are separating the signal, we are separating this in two part. The yt is combination of x and signal and noise, which is going through a filter response. So filter response hx and h and n and h, so nt convoluted to ht. I'm trying to writing in a separate way so that we can write signal and noise separately. That's actually the so this is actually signal and noise. So that actually I'm writing it separately so that I can derive their value. So this can be write as a receive signal rt. So rt is this one, which is actually after here, here rt. Okay, so for our case, this is a signal. What will be the signal then? So this is the signal. So let me write the signal part again, here. Signal, let's say signal. We are actually doing everything for first waveform. You see, this is actually the first waveform. This combination, this is actually the first waveform. So we can do, actually we can give a notation x1. Actually x1 will mean the first waveform, x2 mean second waveform, like this. Okay, so this will be let's give y1, then this is r1. Okay, okay, so signal, signal for x1 part, signal. What was our signal? Our signal was this one, xt and ht. xt is so we are dealing with signal, xt is a1 p1t plus a2 p2t convoluted to ht. These are signal part, right? Okay, so the equation will be minus infinity to plus infinity, a1 p1 tau plus a2 p2 tau, so on. So here this is actually h1, h1t. So h1 t minus tau, t minus tau d tau. Okay, so so h t, we know that h1 t was p1 t minus capital T minus t, right? Let's see. Yeah, h2 this, right? So what will happen with h1 t minus tau? So it will be p1 t plus tau minus t, h minus tau. Okay, yeah. So so we can read. I am rewriting this one because I need to change the t. So sampling, you see, we will be this signal rt is sampled here, right, at sampling t. So sampling at sampling at t equal to t at this frequency, this signal becomes, so we can rewrite minus infinity to plus infinity p1 p1 tau is to p2 tau p1 tau d tau. Here all the t will be tau. So this like t will be replaced by capital T. That's why actually this t and this t, they are replaced. So they will be crossed. So tau remains. This tau remains. So this is the tau. Yeah. Okay. So we are multiplying. This p1t will be multiplied with this one. So we have minus infinity to plus infinity. A1. So p1 p1. So p1 square tau d tau plus a2 here minus infinity to plus infinity a1, sorry, a2 and p1. Oh, a2 is already here, I write it, we don't have to write it here. So this is p1 p1 tau p2 tau d tau. You see the inner product will be 0 and this is actually ep, right, power ep equal to 1. So this will be a1. Okay. Okay, so that's actually the proof that we write. I write it earlier, right? So you see, a1 ep is 1. So actually, this is actually nothing but a1 plus n tilde. This will be actually a2 plus n tilde, n2 tilde. Okay, of course, it's good that we learned it. So this is R1. We find it this value. Okay, good. So the we find this one. Okay, this is actually the proof of the previous statement. Now for optimal detector, so we will actually start detecting it. So optimal decision rule or detector decision. So for that R1t has to be greater than 0, which will decide that A1 is A. You see, A1 has two possibilities, plus minus A. This possibility, right? A2 also two possibilities, plus minus A. Which one is what? So this will give this decision. Okay. So and the opposite one, if R is less than, so R1 t is less than 0, this will decide A1 equal to minus A. So here we are doing nothing but getting the threshold, right? We get, okay, this is the threshold value. That gives our optimal decision. So we see the, you see the each, for example, if we summary, make it summary. So yt, this one, the one we draw it here. This one. This is for single branch, like ideal cases. For QPSK, it is little bit different. What happens in QPSK? There are always two branch of signal. Here, you see whatever we did here. See here there are two match filtering. Match filtering if it's H1 or if it's H2. So that's why. So the match filter H1 T, or it can be match filter H2T. So match filter H2T. Of course, it passes through this match filter where P1 equal to T minus T and P2 equal to T minus, sorry, not equal to, P2 equal to function of T. Then this goes to the sampler at a sampling T. So T will be T will be capital T, and then the receive signal R1 T, receive signal here, this will be like R2T. There this thresholding happens. This, it will be plus a minus a, so it will be minus a or plus a, or something here minus a plus a. So this is the threshold. You see, for all these cases here, actually in the previous derivation, we actually gone through with a single branch, yt, then we took h1t, then t equal to 2, r1, then this thresholding. This is similar for the second branch, the similar solution, right? So this is the QPSK detection, schematic for the QPSK detection. So this is a schematic of QPSK detection. Okay, so we figure out the transmitted signal. We figured out the optimal decision rule. What remains? We now have to find the bit error rate. Okay. Okay, let's find the bit error rate. Okay, so bit error rate of so here you see we had two channel 1, channel 2. Okay, so we had to we can calculate bit error for individual channel. So bit error of the first channel will be what? Will be bit error first channel is, for example, PE, probability of error of QPSK. QPSK. Okay, I'm not writing it here, but it will mean it will be PSK. We are deriving it for PSK cases. So it's nothing but the Q function, nothing but the A by square root of n0 by 2, which is actually A also. We know A equal to square root of EB. So we can write Q equal to twice EB by n0. This is for what? This is for first channel, like any of this channel, or it will be same as this channel, whatever. Now you see this is actually similar to BPSK, right? Similar to BPSK. Okay, so let's say this is first channel. For channel 2, if we would consider it for channel 2, it would be the same one. So we are not doing anything, deriving by n0. So channel 2. So for channel 1 and channel 2, is similar. So PE1 equal to PE2. The error is same. Okay. Now this is bit error. Huh? For QPSK, we are actually concerned for the symbol error rate. So what is the symbol error rate or overall symbol error rate? Because we know that in QPSK there are two symbol, right? So what is the symbol error? Symbol error is nothing but the probability of symbols in error, right? Okay. So symbol error rate, how to find the symbol error rate? So symbol is in error is in if either bit A1 which is in channel 1 or A2 which is in channel 2 is in error. So you see in the channel, if because they will be combined together, because they will be combined in the receiver. So if there is a error in this channel, then the symbol will be in error. If there is a bit in this channel is error, then the symbol will be in error. So either these or both are in error, the symbol will be in error. So this is a condition: either A1, either A2, or A1, A2 both are in error, then the symbol will be in error. So we already know from these previous cases that uh, PE, probability of error of any channel. So okay, probability of error of first channel. Okay, first channel is PE, right? Which is actually this one, PE. Okay, we gave it name PE1. Okay, but PE1 equal to PE2 equal to PE. Okay, it's same. So we don't write it PE1. So probability of first channel, probability of error of the first channel is PE. What is the PC? Probability of the correct. Probability that the A1 is received correctly. Probability of first channel, PC of first channel will be what? 1 minus P. Right? This actually gives us what? This gives us actually the probability of A1 is received correct. Correct. Right? Okay. Now, similarly, that PC of second channel will be also 1 minus P. Right? Okay. So, what is the probability that the both bits A and A1 and A2 or both channels are received correct? So, what is the probability? So, probability that both bits A1 and A2 received correctly is nothing but the multiplication, right? Is nothing but the multiplication 1 minus PE into 1 minus PE, PE equal to 1 minus PE square, right? How we find that? Actually, we find that, for example, here both probability for A1 and N2, they are independent. If they are independent, we know probability of two independent event A and B, their combined probability will be PA of PB. Probability A, probability B. That's why we have this formula. Okay. Now this is the probability that both bits A1 and A1 and A2 received correctly. What is the opposite? That probability that both A1 and A2 in error, which is actually, we know, which is actually nothing but 1 minus this value, right? 1 minus PE square. What would be the value? So it is actually twice PE minus PE square. So you see, we find the probability that both A and B, they are independently, they are in error. Both, of course, they are independent. We know they are independent. Okay, so we should give it to name. This is also probability of error. Okay, so we can write what is a PE? PE that twice PE and PE square. We know the individual PE, PE, which is actually this individually. So we know we can write twice the Q function twice EB by N0 minus Q square twice EB by N0. So this is the overall symbol error rate. So this is the overall symbol error. Okay, we'll do a little bit modification here, like simplification. For example, for very high SNR, which is SNR means what? SNR means like EB by N0. For very high value of N0, the Q of EB by N0, this value is much lower than 1. If it's much lower than 1, then Q square twice EB by N0 is much lower than Q of twice EB. Okay, so just things will be very similar. So we can write the PE approximate quantity is the twice Q square root of twice EB by N0. So this is actually the overall symbol error for QPSK signal. So this is actually overall probability of symbol error of QPSK system. Okay, that's all. So we find the QPS probability of symbol error rate of a QPSK system. So following the same procedure of the previous, we completed the complete analysis for QPSK. That's all. Thank you. Assalamu alaikum.